Hello.
Hello.
Dr. Brown, how are you?
I'm good. How are you today?
Good, good. Thank you for making time to do this.
Absolutely.
This is wonderful. I'm Daniel Pack. I am serving as the Dean of the college, and I'll be introducing you.
Okay, great. Thank you. Hi, Dr. Nassab.
Hello. Do you see anything in my background that may be familiar?
Let's see. Is there something blue back there? Oh, I see an enemy in the corner.
Yeah.
Very nice move, Dr. Nassab. We'll give everybody a few more minutes or a couple more minutes to jump on here.
So, Dr. Brown, are you still serving as the department chair, or did you just step down?
I just stepped down August 1st. Yes, I served 9 years, so I paid my penance. No, it was a good run. We've had a lot happen and a lot of good things are coming in the future. We break ground on a new building December 6th. So that's
Great. Congratulations.
Thank you. That was a highlight. I worked hard to raise money for that. So now I'm just going to hand the keys to somebody else.
That's good.
All right, so it looks like it's 3:15, so we can go ahead and get started, and I'm sure some other students will be popping in here as we go.
Okay.
So just a couple housekeeping items for everybody before we get started. I think when you all joined, you were automatically muted. So I think that'll be the best setting for the bulk of our time here. And then we'll have some question and answer time at the end, so you can unmute yourself or use the chat box, and you can put your questions in there at any time during the presentation or during the Q&A part. Otherwise, this is recorded so that we can share it afterwards, so it'll be available. So without further ado, I will ask Dr. Pack, our dean, to introduce our speaker, Dr. Brown.
Sure, thank you. Thank you, Dr. Brown, for being here. I think our students and our audience is in a treat to hear from Dr. Brown today. I'm just going to give a very brief background of Dr. Brown, and then I will yield the floor to Dr. Brown. Dr. Heather Brown from Middle Tennessee State University has been there since 2001 and served as the department chair of the School of Concrete and Construction Management until just this August. Her technical experience includes 5 years of material testing, research for the Tennessee Department of Transportation during graduate school. She has authored and co-authored over 30 papers, and Dr. Brown has been awarded a recipient of Outstanding Grantsmanship, Overall Excellence, MTSU Faculty Who Make a Difference, and has been recognized as an influential woman in business in Rutherford County in 2015, and National Concrete Construction Most Influential Person in 2017. She's a fellow of ACI and inducted into the Tennessee Concrete Hall of Fame in 2019. She teaches and research in the areas of material optimization, byproduct utilization, construction tolerances, concrete troubleshooting, and also on recycled concrete aggregate mixtures and full depth reclamation with cement stabilization. Dr. Brown's academic preparation includes a Bachelor of Science degree in Civil Engineering, Master of Science in Civil Engineering, and PhD in Civil Engineering, all from Tennessee Technological University. Today we are very fortunate to have her to present to us under the title of Build with Strength, Innovative Materials for Concrete Applications. So please help me to welcome Dr. Brown, and thank you for being here.
Thank you for that nice introduction. I appreciate the invitation. I know that you guys look for speakers for your series, and Dr. Nassab was kind enough to mention my name. So thank you for including me in this series. It's hard not to be in the room with everybody. I love engaging the audience and finding out other people's backgrounds, because I continue to want to learn from others and see, what things are happening in other institutions. And so, as you can see from my background, I'm been at MTSU a long time, so I'm clearly been true blue for 20 years, but I did hail from Tennessee Tech University. So I'm definitely a Tennessee kid, but I thought I would start with a little background even beyond my academic preparation, because I get asked the question a lot, how in the world did I end up studying concrete? As a female, that was probably unusual at first to most. I find that more females are entering into construction, into concrete engineering more and more each day. So that's exciting. But as a child, I was a child of the 70s and 80s, and I was, spent most of my time outdoors. I loved building. I was a master fort builder. I could build blanket forts and snow forts and leaf forts. And I really felt like that catapulted me into the love of materials. I was a kid that played in the dirt a lot, played with friends in the neighborhood. And I always found myself building something. If it wasn't building it inside out of Legos, it was building outside with some construction material that I could, pull from the garage. So I know that's where my passion started. But when I got to college, I did declare civil engineering. I knew that I belonged in that industry just from what I read about it. I didn't know a civil engineer. I had never met one. I didn't know what the career would hold for me, but you read the description and it just really sounded a lot like me. I did go to a high school that gave a test in 9th grade called the ASVAB test. I grew up on military bases, and they would give an ASVAB test. And that test actually told me that civil engineering was a good match for me. So I believed it and ran with it. And I discovered concrete my second semester in college, actually. I was fortunate enough to be a part of a student competition team. So I still today mentor student competitions, because I really believe in the difference it can make in opening somebody's eyes to what other students are doing in other schools, but also just the creativity and innovation that is happening at universities. But I was the lucky recipient to be on a team that was looking into lightweight aggregate. And, back in the early 90s, lightweight concrete was still rather new. It hadn't been tried and tested on job sites yet. People were still trying to understand the impact that lightweight aggregate could make on a job site, and how does an engineer design lightweight mixes. And so we were just tasked with making a mix that would get ultimate strength. We were all going for the highest strength we could get. And our little team from Tennessee Tech managed to win first place by getting almost 20,000 PSI out of our lightweight mixes. And back then, that was an amazing number to get with really very little knowledge about what the material would do. So I definitely attribute that experience to also being a jumping off place for getting into this industry and really loving materials and the science behind all the different recipes. So a lot of my presentation is about all of the different materials that not only have been around for 20, 25 years, but what's happening today that we can make a difference by just knowing about them and exploring them further. There's still a lot of R&D to be done. And so hopefully there's some folks on that are graduate students that can really foster these ideas and take these ideas to the next level. I can definitely see this generation and the generation beyond really making some of these materials turn into everyday uses. We're still on the cusp of so many great discoveries. I do believe that once I finished college, I really thought that I was going to continue my R&D with TDOT. That was the plan. And the program here at MTSU started, and they found me in a lab at my university and said, why don't you come be a teacher? So at 25 years old, I was hired. Dr. Nassab was actually one of the gentlemen that hired me and believed in me and put me on staff here at a really young age to steer this concrete program. So again, concrete's been part of my life for a long time, and I hope to share some of that passion with you today. So I like to kick off my concrete presentations with a pump up video. I really believe that there's a lot of things about this material that are misunderstood and maybe not even appreciated. So I'd like to start with that. This is a cool little video to get you excited.
Dr. Brown, is there supposed to be sound associated with this video?
There is. You're not hearing it?
No, you need to share your sound system
All right.
with us.
Sorry about that.
If you look on the top menu where it says more and you click on that,
Yes.
it should be
Okay,
right
thank
there.
you. I've not had that problem before. Sorry about that.
If you're an architect, engineer, and about strength.
Thank you.
No, not that kind of strength. The kind you see in buildings, condos, hospitals, homes, skyscrapers. What gives them super strength? Ready mixed concrete, one of the most durable, amazing, impressive materials on planet Earth. Concrete gave America its spine. It allowed us to grow, prosper, and stand tall. That's because concrete lasts forever. Just ask the Romans. True strength doesn't burn, warp, deteriorate, rot, or yield. In fact, concrete gets stronger over time. Imagine that. And for those who think concrete isn't flexible, it can be molded into any shape you can think of. Strength is innovative, beautiful, practical, smart, quiet. Strength doesn't bow to the elements. It thumbs its nose at Mother Nature when she's angry. And that means it's perfect for low to mid-rise structures. So if you're an architect, engineer, investor, legislator, start from a position of strength. Build with concrete. There's no stronger investment.
So is everybody excited about concrete now? So really the video alludes to this. There is a history of concrete that's been around for a long time, and it actually gave credit to the Romans, which is really where we have adopted most of our recipe. But I can't go forward without giving its proper notification to the time period, the Neolithic age, where the Egyptians built the pyramids. It's not the concrete recipe that we're used to today. It was much different, but no doubt it still has the long-lasting durability that we're so accustomed to with concrete. Now, the real recipe that we have adapted over now centuries is the Roman recipe. And you can really look at its basic components, and it's very similar to what we do today. When I'm talking with K through 12 children, I talk to them about the recipe in the terms of cooking, because I do believe that concrete is a version of cooking for our built environment. And what's wonderful is that there are so many different recipes that perform so differently from application to application. And so you really can take this recipe and make it your own every time. Every time you mix, you can adjust something or tweak something and really get a different performance value. But basically, the Roman recipe involved similar ingredients, sand and water. Their version of cement, because cement hadn't been invented yet, was combining volcanic ash and lime. What I always like to mention too is modern day concrete is full of chemicals. When my students are taking classes, it's really important for them to have a great handle on chemistry. And they don't always understand why that is, because chemistry doesn't seem like it goes with concrete on the surface. But actually chemistry is really how the entire cement hydration process occurs. But the other part of chemistry with concrete is all of the different admixtures that we now enter into a truck of concrete. So you're familiar with ready mix trucks driving down the road and the rotating drum. There is not a load of concrete that does not leave a plant now without some amount of chemicals added to it. Back in the Roman days, those chemicals came in the form of animal fat, animal milk, blood, and hair. And we're using derivatives of those same things now. Fiber reinforced concrete is essentially an advanced version of goat hair concrete, but it's working. And the testimony is really dating back to the Roman recipe. So another adage that I like to point out is that concrete is the most used building material in the world. It is the second most used material to water. And so a lot of people don't realize that they're consumers of concrete. I kind of compare it to drinking a Starbucks. You don't necessarily think about consuming concrete like you do your daily Starbucks. You don't brush your teeth with it. You don't dress in it. You don't shower in it. So you're not consuming it like water or some other important ingredients, but you are consumers of concrete by just living and breathing in our built environment. Going to school every day, working, driving, going back to home. There's a concrete element or component everywhere in your life. And even people who are in engineering and in the science field don't realize how much they're surrounded by concrete. So I looked up the 2020 statistic because it changes every year. But in the year 2020, you're consuming about a half a ton, a little over a half a ton of cement is consumed by you by just being part of the per capita. And so that's a lot of cement. I mean, if you think about it in bags of cement, you're talking about each bag weighing about 100 pounds. So you'd have to go to Lowe's and buy yourself about 12 bags of these 90 pounds or 94 pounds of cement, and that's what you're consuming. And that can be new construction, that can be repair and rehabilitation, but essentially this is being utilized and sold and manufactured in the world. And this statistic actually accounts for the US population. But unfortunately, cement gets a really bad rap for its environmental impact. And so I spend a lot of my energy now trying to help the industry find ways to be more environmentally friendly. I'm on a lot of different committees that really focus on that footprint, the carbon footprint of creating concrete. And cement is really the nemesis of the recipe. It's the most important ingredient that we can put in concrete, but it also is the one that's causing so much heartache in the carbon footprint discussion. So I'm going to compare it to a couple other industries just to give you some perspective, because I do think sometimes cement and concrete really get the finger pointed at them a little too much sometimes. So I'll just compare it to a couple other industries. The automotive industry creates about 28% of our greenhouse gases currently. And the agricultural and food processing industry, I'll call it the cow industry, essentially is creating about 14.5% of our greenhouse gases. So cement's on the list, and it still is definitely an industry, a manufacturing industry that is contributing to greenhouse gases, but it is running around 8%. So it's not at the top of the list, but it's on the list. And the fact that it's even on the list, we've got to pay attention to it as a country. So how can we do things just slightly different to cut down on that impact? So there are a lot of recycled ways that the industry has been utilizing for a couple of decades now, and there's more coming. I really feel like some of the current ones I'm going to talk about really are just scratching the surface. And so I'm very hopeful that the initiatives that have been started by particularly the architects and the owners are really demanding green buildings. As you know, green buildings has become kind of a hot topic. People want to build a green building. They want to have a certified green building that they work in. Potentially even one day we'll get to LEED approved green building homes. There's still people that want to live off the grid and to not have such a big influence and imprint on society from an environmental impact. So there's so much more to do, but I think the concrete industry is really trying to address this from several different angles. One of those angles is tried and true and has been around for quite some time. When I started my career, fly ash was already a well-known material, and many of you are familiar with fly ash. TVA is right down the street from you, and you know that they spend quite a bit of energy literally trying to figure out what to do with all of their fly ash byproduct. So I bring it up again because unfortunately fly ash is now a hot topic again, and not for the right reasons. Fly ash has had kind of a storied past. There's been some strategic spills over the last couple of decades where some energy companies have not contained their fly ash properly. There has been some contamination in waterways due to not storing fly ash properly. But really the long story of this is that we're not utilizing the fly ash in the way that we could in order to cut down on both storage concerns and then also trying to make new landfills to store this material. One of the TVA plants close by to MTSU is TVA Gallatin, and they have over 400 acres of ponds filled with about 40 feet of fly ash just sitting in sludge ponds. They've been allowed to do that for years by the EPA. It was condoned and approved, and they've kept everything within their confines of their area, so they've not breached any waterways or caused any problems. But the fact remains that they have 400 acres of waste fly ash in ponds. And that is not what EPA wants to condone in the future. They would like landfills and energy companies to try to eliminate some of these storage facilities and figure out better ways to use fly ash. So although fly ash works so well in concrete because it's so similar to the cement powder in its form. It does form different chemical compounds, but it is very similar in how it responds to hydration. And so we can't do without it really going forward. It's something that we need to keep in concrete, but we're going to have to, this generation in particular is going to have to work with these private energy companies to ensure that this product is made available. Because the easy thing to do would be to shut your doors and put it in the landfill and not worry with it. But by selling it, you have to make sure that it's available and that you're processing it in a way that allows that byproduct to actually be consumed and used. So I don't think we're done talking about fly ash. Right now, a concrete producer probably puts on average about 20% fly ash into a mix to replace cement. So every time we can replace a portion of the cement, we're cutting down on our carbon footprint. And fly ash, because it's a byproduct, is not increasing the carbon footprint of the concrete ultimately. So as you can see, pretty similar material. Fly ash is known to be a pozzolanic material, which means it does not react with just water. If I added water to cement, an immediate chemical reaction would occur called hydration. Several chemical compounds would form. That does not happen with fly ash. So I cannot make 100% fly ash mix without doing some other chemical composition changes. So I have to substitute this for some portion of the cement. Fortunately, there's a lot of engineers that have figured out how to supplement even up to 75% of the cement with fly ash. So there's big benefits in trying to keep fly ash a readily available byproduct. And we're not the only state suffering from this. North Carolina, South Carolina, there's other large energy coal producing states that are dealing with fly ash issue. The good news is that there is a technology out there that will reburn waste sludge ash that has been basically deposited into ponds. It will reburn it. So there is some energy involved in getting that product to be a better product, but it's minimal energy to be able to turn waste ash back into good fly ash. And so that's the hope, is that both government and private industry will work together to bring this product back to its heyday. So the other product that's actually gaining a lot of traction right now is slag. Because there is such a fly ash shortage, we're having to rely on other products and other powders, if you will, from other industries. And one that has been around now for about 20 years is commonly known as slag. It's got a long proper name, ground granulated blast furnace slag, but everybody in the industry calls it slag. And it's a white powder that comes off of the smelting process. So anything that has to do with manufacturing metal, the automotive industry, for example, there's going to be some smelting involved in some of the different materials. And so as they're going through the smelting process, this fine particulate does come off and is a waste product to the industry. So we're able to collect it and grind it down a little bit finer, more similar to cement, and sell it. And it is cheaper still, just like fly ash, it's cheaper than cement, and it cuts down on our carbon emissions as well. So it really is a great product. It has a higher reactivity than fly ash. So I actually am going to get more strength out of a slag amended concrete. So a lot of producers really like getting slag because they're able to sell it for both residential concrete and then high-rise commercial concrete because of the strength characteristics. So the third powder that I'll mention is one that is really pretty special. Unfortunately, it's actually a little bit more expensive than cement, but it still is a byproduct. And so it is still cutting down on our carbon footprint and our greenhouse gas emissions. So we're thankful for that part of it. But the industry that this sources from is the industry of silicon dioxide manufacturing, which is really kind of a precious metal or a precious compound. So this precious compound is used in the list that you see here. I mean, we use silicon dioxide in our solar panels. We use it in adhesives, lubricants. You can see the list. It's a very critical list to the function of society. And so because of that, it's an expensive process. And naturally, even the byproduct they have figured out is special to concrete people, so they charge a little bit more for it. So this dust comes out kind of a bluish gray, and it's used in high strength concrete. So for example, in downtown urban markets, you're going to see a lot of silica fume concrete. And it's always a little bit darker too. If you ever happen to notice a really dark gray concrete as you walk maybe in a parking garage, that's probably because it's silica fume concrete. It dries darker gray, and it's kind of a bluish tint to it as well. And what's unique about silica fume, it is ground 100 times finer than cement. So if you just think about it from a mechanical perspective, you're now filling voids that cement particles couldn't have reached before. So the density of the concrete is so much higher. And so that's really what's giving it so much of the strength. It's not that there's a chemical reaction occurring as much as there is a mechanical reaction occurring. So you just have a tighter packed, denser concrete that's near impermeable to things like de-icer salts. So if cars are bringing de-icer salts into the parking garage, a silica fume concrete is going to manage that so much better because the de-icers are not going to melt into the concrete. One other note about silica fume is more is not better. A lot of people think that, oh, if it's really strong, I'm going to use 20%, 30%, 40%. You actually are limited just by nature of the material itself to 10%. And the reason is, and I've been on job sites where this has actually happened, silica fume creates a very sticky concrete, almost like peanut butter. And so as finishers are finishing the concrete, it literally will suck the tools right out of their hands and suck the boots off of their feet because it's such a dense, sticky mix. And so there's advantages to that because it's creating a dense concrete, but there's limits to how sticky you can really make concrete before it's going to be able to be pumpable or come out of a truck. And the last kind of recycled product I'll talk about, and then I'll move to some other topics, is recycled glass. And I wanted to bring this up because we're actually not doing recycled glass justice right now. This is an industry that is just on the verge of being such an important product to concrete, but we cannot get enough manufacturing facilities to take their recycled glass, their leftover glass, and do something with it. They're not sending it to the right facilities to be processed. And us as recyclers, when we throw our bottles into the recyclers, those bottles aren't even making it to the proper place as a waste stream for our industry. So we're probably a decade away from truly being able to utilize recycled glass to its fullest extent. But there are people that are trying. In the state of Tennessee, we finally have one company, it's in Jackson, Tennessee, that is processing glass for concrete. And it's doing it for a lot of industries. So it's not just doing it for this industry, but there is a process in taking this glass and actually chemically cleaning it so that all the residue that's from the actual glass product through, whatever it was, if it was spaghetti sauce that was in there, a jar of olives, there's going to be a residue that's on that glass. And so this company takes it to the next step by chemically cleaning the glass and then processing it down to the size that we need. And you can really process it down to any size. This would be a replacement for aggregate. So instead of using natural aggregate, you would use a recycled glass aggregate. And so this creates obviously a very architecturally pleasing concrete. It's very popular in the decorative industry, countertops and floors. And we're really seeing this take hold because owners want this. This is a look and a feel of concrete that is really pleasing. But if you get down to a smaller size, there's not as many applications that are being used yet. One that I've been a part of here at MTSU is doing recycled pavement, recycled glass pavement. The big advantage of this is not only is it using recycled glass, but this is actually permeable pavement. So it's for very unique applications. You're probably familiar with permeable pavements already. There's pervious concrete, there's actual permeable pavers, there's porous asphalt. So that's been on the market for a while. But this is recycled glass permeable pavement. And we placed about 8 parking spots here in Murfreesboro to do a research study. And it's very interesting because it shows up in a very different trucking mechanism. You don't actually mix it at a concrete plant and truck it to the job site. You actually mix it in a mobile mixer. So the glass is in the truck, and at the last minute, the glass is coming down the chute. It intercedes with an epoxy material. So this epoxy material coats it just enough to where the glass does stick together, but leaves several voids so that it's still permeable. So this does not have cement in it at all. It is literally just glass and epoxy. And you're only putting it down at about a 2-inch lift. So underneath this glass, what you don't see is probably about 10 inches of 57 or 67 stone, which is just going to give you your drainable base layer. This is not for high-speed traffic. This is for parking lots, bike paths, pedestrian walkways. So there's limited availability or access that you're going to have to this. but I'm really seeing this being a great way to utilize recycled glass. And I put this little statistic in here just to give you that perspective. So 1 square foot of this permeable pavement costs or would use 90 glass bottles. So imagine all the recycling that we're trying to do. So much of that glass is still ending up in the landfill anyway, but 1 square foot of this would be, you know, an equivalent of taking 90 glass bottles out of the landfill. So I do feel like that's going to be a very popular technology going forward. But for now, we're just trying to figure out where can we get this, who's processing it down to the size that we need, and how do we get it on our job site. So definitely a to be continued technology. And just the last point on glass, you can grind glass down to a powder. So I've already talked about several powders. This one's not readily available at ready mix plants yet. It's really a custom concrete recipe ingredient. It was actually used in the construction of the Freedom Tower in New York City. It was used in the construction of the Burj Khalifa. So there are projects that are utilizing glass powder, but it's on an as needed basis. So I'm really hopeful that this is another powder that we can add to our toolkit when we're looking at trying to cut down on environmental footprint. All right, so I would like to talk a little bit about some applications. So one of the things, I'll skip over and come back to homes. One of the things that I'm really excited about as we look at how to cut down on our environmental footprint is a very brand new process called Carbon Cure. If you notice this map right here, this is the state of Tennessee here in the middle, and then you can see Kentucky over here at the top. So Middle Tennessee has embraced this technology of harvesting, essentially they're harvesting recycled carbon dioxide from other industries, trucking it in something like a gas tanker, and then injecting recycled CO2 into brand new concrete, fresh concrete, as it's being delivered to the job site for a brand new construction project. So we're taking sort of the emission waste from other industries, injecting it into new concrete. And the beauty of all of this is it's mineralizing into the fresh concrete and creating strength within the concrete without having to add extra cement. So a concrete producer can actually cut down on their cement content around 5 to 8%. So it's not a huge number, but it's something. So they can cut down on their cement content and then in turn be environmentally friendly by helping other industries get rid of their waste carbon dioxide. So already we're seeing Middle Tennessee take advantage of this. You can see by the map, there are some in North Georgia and North Carolina. So it is spreading. There's some statistics here talking about how many carbon dioxide emissions have been saved so far. So 90,000 tons of CO2 emissions by this process alone. And this technology has only been around now for a little less than 2 years. So they're making a huge impact on trying to figure out ways to cut down on cement content, but also help other manufacturing industries. I will give you a quick chemistry note on this because it'll come up later in the presentation. When CO2 is injected in concrete, you might wonder, how am I getting actual strength? What is happening, it's combining with calcium hydroxide, which is a naturally emitted out of the hydration process. And when those two things meet, you get what's formed as calcium carbonate, which is essentially a form of limestone. So that's where the mineralization process occurs. And that's where CO2 is coming in handy to be able to cut down on the cement content. So I can get strength out of this process without having to add the extra pounds of cement to get me to my target PSI that the engineers have. So just a little close-up view of where we're seeing plants. So here's Greater Nashville, and you can see all of the plants now that I can order Carbon Cure concrete from. So we're actually going to be doing some Carbon Cure placement here on campus very soon, so we can kind of demonstrate it. And the concrete doesn't look any differently, so nobody would really actually know that there's Carbon Cure in it. But the idea that you're creating a greener concrete is really great news. So on that same note, I mentioned that calcium carbonate is a weakened form of limestone that is formed inside concrete. So there's another group that has come up with what's called self-healing concrete, and we've worked with it here in the lab as well. It was a group out of Italy, actually, that came up with this concept, and they've come up with quite a few creative and ingenious concepts with concrete. But the concept of being able to heal your own cracks was something that was the goal in mind. And what they're essentially doing is injecting the concrete with a bacteria that will then create that calcium carbonate. So what your aim is to get the concrete crack to seal itself with its own mineralization. So here's kind of a before and after picture of this process. And I'll tell you the latest on this is now they're injecting it into fresh loads of concrete. So you do not have to wait for the concrete to crack for this to work. This experiment here that you're seeing, this is a before and after picture here on the left and a before and after picture here on the right. So a crack formed and they injected that crack with bacteria that contained the right microbes that would create that calcium carbonate. And when oxygen and water hit it, it started creating that limestone and filling in the crack. And so, this is only after 100 days. So after 100 days, this bacteria took hold of the concrete and basically self-healed itself. And this is just another example here on the right. So what was early learned was that you could do this after the concrete cracked. What we've learned since then is you actually can inject this bacteria into the concrete in production, deliver it to the job site, and then at any point in the life of the concrete, after it cracks, it will self-heal itself as long as it has a moisture present. So it does need water. It's almost like watering a plant. You have to have some amount of moisture available and oxygen. So for certain environments, it wouldn't work, but for certain climates and certain conditions, exterior concrete, it would absolutely heal itself. So on the same note, you have self-healing concrete. You also have smog-eating concrete. I personally have not been on a large project on this. I've been on a research project and seen the application, but they are already building roads in St. Louis, in Detroit, in Chicago. Some of the Midwestern states have taken hold of this. There's a lot more concrete paving in the Midwest than there is here in the Southeast. We are typically an asphalt state. And so smog-eating concrete hasn't really taken hold in Tennessee, but in the Midwestern states where they have a lot of concrete paving, we've seen this quite a bit. So I'm eager to get to a project where I can actually see it in person. But the concept is really quite wonderful. The group that came up with it originally came up with it because it was about self-cleaning. The product that they're using is titanium dioxide. If any of you have a fence at home that is that white fencing that you get from Lowe's or Home Depot, it's that plastic fencing that you're kind of used to seeing now around suburbias. If any of you have that product, there actually is a titanium dioxide paint that is used on those white fencing in hopes of keeping it cleaner. Now, I'm sure you've still pressure washed your fence a couple of times since you've had it because it doesn't keep it perfectly clean. But the idea is this titanium dioxide paint helps to keep that white as bright as possible. So that concept then translated over to the concrete industry, and the concrete industry started putting it in their concrete, hoping that they could keep concrete whiter and brighter. Architects really like it because if they want to design a building that is a little brighter and whiter with, let's say, slag concrete or white cement, having this titanium dioxide in there helps keep their concrete a little bit clean. So through all this, they learned that by self-cleaning concrete, you were actually turning smog into chemically another product. So let me show you that chemical reaction. So essentially, if you have your concrete road right here, so this gray represents the concrete road, and you have injected titanium dioxide into the concrete. So that titanium dioxide is available at the surface. So as smog is coming down onto your pavement, basically out of the back of a car, then it hits the pavement. Sun reacts with this as well. There's active oxygen there at the surface. There's a chemical reaction that occurs that turns this into nitrate, which is a basically naturally occurring element or compound in the environment that helps feed plant life. So now you get this beneficial chemical reaction to occur, and now you don't have smog affecting the environment or turning our air much less cleaner. So that nitrate product is a benefit. It's taking smog and basically catalyzing it into something else. And the great benefit is you actually get cleaner concrete. So the concrete on the left has been treated with that titanium dioxide and the concrete on the right has not. And they ran trucks past this It was like a closed circuit where they were running trucks right by this particular research site to prove that the smog coming out of large trucks colors concrete, turns concrete an even uglier color than the gray that it is already. And the titanium dioxide concrete not only is turning that smog into nitrate, but it's keeping the concrete a wider, brighter color. So I think you're going to see more of this. Here's the bad news. Titanium dioxide concrete is about 7 times the cost. So our DOT is not running out and buying titanium dioxide smog eating concrete because it is more expensive. So all the placements that I mentioned to you were really research-based placements, the Detroit and the Chicago and the St. Louis placement. It was really funded by research dollars to see if this really is going to make a difference and make those cities cleaner. If the data starts working in our favor, I think we will see it in our area. I think it's going to be a big benefit. This smog eating concrete will work up to 8 feet in the air. So any concrete surface, whether it be horizontal or vertical, up to 8 feet will clean the smog coming out of the back of vehicles. So it really could be a game changer. There are lots of people now researching bendable concrete. Bendable concrete, really to break it down very simply, it is just nano-sized materials used to make the same recipe of concrete that we're used to. So instead of large aggregates and large sands, you use very small aggregates and small sands. Instead of having a powder that's ground to 300 micron, you will use powders that are ground to 1500 micron. So you're basically taking every known material that you like about regular concrete and you're turning it into much smaller particle sizes. And it's really like the silica fume discussion I had earlier. As you ground something finer, it packs tighter, therefore creates a matrix that is both impermeable, but in this case, something that doesn't crack as easily. So bendable concrete is known around the industry as ECC, which is engineered cement composites. And there's a lot of people looking at ECC. It's really going to have a great impact on some of our specialty products, on overlays, anything that takes a lot of high stress and needs to be able to bend. I see it being very useful in seismic zones because you're just not going to get the failure mechanisms that we're so used to with concrete. And so this is going to be a product that I think continues to gain traction. Just like smog eating concrete, though, it is higher priced. They've gotten this down to 4 times the price of normal concrete, but that's still 4 times the price of normal concrete. So no doubt this is not something that a DOT or an FHWA is running out and buying off the street. This is still a technology that is still outside of the purse strings of the government, but definitely in private industry, we're seeing some placements going down. So that's good. And just kind of some fun concrete. There's concrete now that you can see through. It's called translucent concrete. You see shadows essentially. They're using this in office buildings in Europe to try to improve worker morale. Lots of people don't have windows in their office. And so the thought here is, okay, you don't have a window, but now you have this shadow effect of cars passing by or people passing by. And they've done a few studies and it actually is improving worker morale and worker attitude. So we're not seeing it in a big way over here yet. There is a company, BASF, Chemical Admixture Company, that has purchased the rights to the material that is used to create translucent concrete. So it is in America now, and they are selling it to certain projects. So I think this is also going to be a product that we might see more of as they look at the benefits of it. Right now, I think the understood benefits are a little slim. Worker morale is important, but are there other things that you can do with translucent concrete that will make a difference? A gentleman that I actually know personally invented this glow-in-the-dark concrete about a decade ago. So pretty interesting there. He's out of Southern California and he was into decorative concrete and he created this glow in the dark. And then really this fiber optic, anybody can do this. You can buy on Amazon right now for $20 a full strand of fiber optic that could light an entire kitchen. But the idea is you could come into your kitchen at night to get your nightly snack. And when you turn your light on, it would turn your countertops on. So your countertops would come to life just like your overhead light would come on. So fiber optic is available really anywhere. It's just getting somebody to cast it into your concrete. But it's a pretty cool concept and it looks really good. I've noticed it in some restaurants already where they have it around some of their countertops. So it's a pretty interesting concept. So I want to get to concrete homes. I really like this topic in the sense that this is also a market that is just bursting at the seams. I don't know how Chattanooga is looking right now, but the greater Nashville area, we're just building homes left and right. Commercial is still strong, but residential just seems to be on fire right now. And not only is it new construction, but it's a lot of renovation. A lot of people are staying where they are, not selling their home, but adding to their home, making major changes to their existing house. And something that people just really steer clear of is thinking about building anything out of concrete as it comes to their home. And I think it's because of this picture right here. I picked this picture because when people think about concrete homes, I think they have to live in something like this. And there's even like a Terminex commercial that talks about how living in a concrete home would be like living in a cold gray box. So, you know, this is not the concrete box that we're really thinking about is the home that you want to live in. There's homes like this out there. There's minimalists out there that choose this as their architectural landscape. But really what I'm talking about is insulated concrete. And we're seeing a lot more of this in our market. And it's really surprising that we're seeing it because normally you see ICFs in a market where there's a lot more hills. So I definitely feel like you've got opportunities in your market. You've got a little more landscape and hills in your area to see more ICFs. So insulated concrete forms are really like Legos to me. I look at them as like styrofoam Legos. They come on the job in long segments. You can pick one up with your pinky. They're very lightweight. They're very user-friendly. Workers love them. The concept really is pretty simple. You stack them and then you fill the core with concrete. So the concrete's not the outside skin anymore, which is why this concrete house ends up being so beautiful, is because you can put any veneer on this building that you want. You can still drywall on the inside, and then you can still put brick and siding and all the things that you love about your normal house on the outside of this. And it's heavily reinforced. That's really where one of the big benefits are, is it's rated up to 200 mile an hour winds. So you're basically building your own tornado shelter within this home as well. So I've been on a couple of projects. We have a couple of good contractors now that know how to build with this. I think that's probably the biggest thing that's holding us back, is having enough contractors that understand ICF construction and how they can save money. I built my house about 15 years ago, going on about 18 years ago. And I priced this product hoping I could build an ICF house. And I could not find a contractor in 100 miles that knew how to build with ICFs. And so there was just a lot of uncertainty about what this product could do and how to build with it. But now it's much easier to find a contractor. And the price is really only about 2 or 3% higher than stick frame. I would guarantee you right now, if you compared the price of ICF with stick frame, I bet ICF would be cheaper because lumber costs have gone so high during this pandemic. But nonetheless, this is a product that I believe in. I've seen it in person. I just toured an ICF hotel. And I really believe in that concept as well, because it's a great way to get a lot of room-to-room comfort, noise reduction, and then still getting that wind resistance. And they're seeing a lot of savings because they're not having to heat and cool their rooms as much because the ICF keeps such a high insulation. You're getting, R50 out of these walls in some cases. It's somewhere between R35 and R50, depending upon the thickness of this concrete wall and the thickness of the styrofoam. You could never achieve that at a normal stick frame and insulation, even going in with, closed cell insulation. It's very difficult to get past an R30. So this is a system that I think is on the rise. The cost is coming down. And it really is easy to build with. A lot of people believe that you don't have contractors that know how to work with it, but you really do. And these are the homes that you're going to end up with. Any size home, it doesn't matter. We're actually working on building a Habitat for Humanity house out of ICF, just to prove that 1,000 square foot house made out of ICF will save the homeowner money compared to a regular stick frame house on heating and cooling bills. And so that's an experiment that we're running right now, because our Habitat for Humanity has finally, decided that they would build one of the houses out of this material. So it's really a great product. Here's an ICF hotel. So it's not just for residential. It's really probably best suited for hotels and schools. Kentucky passed a mandate that all new elementary and middle and high schools have to be built out of ICF. They have to, if they aren't built out of ICF, they have to prove that they are tornado resistant and that they're net zero on their energy. Because you can create a net zero structure with an ICF building much easier than you can with a stick frame or block. And it is really easy to build. So I show a couple females here building an ICF house, but these are super lightweight. And so the workers, the ones that are used to picking up big heavy blocks or forming with big heavy materials, have been much happier on these job sites. And then a pump truck comes in and creates the magic. And I'll be a little bit dramatic, but concrete houses have been in the news a lot in the last couple of hurricanes. This was one of the first pictures I remember back in 2005 when Katrina hit, when you really noticed the difference that concrete could make in a residential environment. We're just not building concrete houses. That's just not the norm right now. So I think that's going to have to change for us to really understand the impact of what hurricanes are doing currently. A more recent hurricane that you're probably more familiar with is Hurricane Michael. Hurricane Michael came through a couple summers ago and decimated the panhandle of Florida. This is actually a beach town that I've been to many times. I've stayed in about 5 different places in this beach town. It's called Mexico Beach. And all 5 places that I rented on VRBO are wiped out. But the news covered this town not only for the tragic loss of people and infrastructure, but for this concrete house. I bet there was 10 stories about this house after Hurricane Michael because it was built with ICF concrete. So, you know, it can make a difference even in the worst of circumstances. And then even more recently, the Bahamas last year was hit by Hurricane Dorian, and there were several concrete houses on that island that survived. And you know, they experienced a lot of loss of infrastructure and life there too. So, you know, really trying to look at what does this mean to us to really move in this direction. And I think it's life and loss of you know, buildings. And we just have to reconsider what we think of when we start building homes. And so these videos really are more about, you know, just that tornado resistant and wind resistant. So that's a normal stick frame house. And that normal stick frame house at a 200-mile-an-hour wind's going to have, you know, a piece of 2x4 run right through it. I'll just mute this and talk while it's going. So this would be a brick veneer on an ICF wall. And you can see that that same 2x4 is barely going to break the brick. It doesn't even go through the wall at all because the ICF wall is solid concrete. And so I think the difference there is pretty dramatic. And I'm sure a lot of you have heard about the movement that stemmed out of China with 3D printed houses. China really has taken this and run with the technology. We're seeing it here in the US with 3D printed houses. There's houses, 1,000 square foot houses going up in a day. I think this is probably yet to be understood about how we're going to truly benefit from this, whether it's emergency shelter that we build, whether homes, real homes that people live in, day out are being built in America this way. But I think the technology is here to stay. I think young people are excited about 3D printed houses. I think the material composition is exciting because you're working with different powders and different chemicals to really make that perfect mix. And then you're working with different configurations. You know, what really is going to work, sorry about that, what is really going to work with a 3D printed house is going to be a lot about the engineering, determining different flexural and tensile and shear resistant as you start looking at orientations of how this 3D printer truly works. Right now, the R&D, if you talk to somebody that's really researching 3D printing concrete, is really about the slumpability and the workability of this material and how it really has to stand up on its own. As you can see, that bead has to be high slump enough, high workable enough to come out smoothly and consistently, but it also has to hold itself up. It has to have some amount of rigidity. And there's a science there. It's not an easy concept. There's really a lot of trial and error that has to go on with the mix design to make that happen. I mentioned fly ash earlier. I bring this up because this is a way that we can use fly ash in a way that's not being used currently. There's a lot of waste ash that is high carbon, and we cannot put high carbon ash in concrete. That is one thing that we know is not allowed. And the reason is a high carbon ash creates a lot of problems with the chemical matrix of concrete. So high carbon ash is really a waste product that just gets straight to the landfill. But MIT is working on a concept where they would power their city cars. The city car initiative came out of MIT, where you have self-driving vehicles that tourists can come and rent for the day and see the sights of, let's say, New York City in a car that is readily available to them, much like the bike system that you see in major urban areas. But the idea is that the road would actually help power the vehicle. So this is still a work in progress. The city cars, they're actually manufactured now and they're available, but how they power those is still being determined city by city. So right now you'd have to have an above grade or above street level powering system to make sure that they stayed on the route that you wanted that car to stay on, because you don't want the driver to have to worry with it. But I think the high carbon concrete is a great concept that we hope turns into something. All right, last two projects, and I'm really proud of these last two projects because I was a part of some of the research on these as well. So one of the things that concrete has been, known to do is turn it into not only a cast in place material, but also a material that you can make off-site, precast, and then deliver it and then make something much faster. You can basically hasten your schedule by having a precast material. So Nashville undertook an initiative where it wanted to repair 8 bridge decks in greater Nashville, and they wanted to do that in 8 weekends. And this was a very aggressive approach because bridge decks do not get repaired in a weekend. Bridge decks get repaired over several months. And the concept of fast fixing a bridge deck was really kind of a new concept. There was only one other state in the country that was doing it. Connecticut was the first state that started doing these fast fix bridges. So accelerated bridge construction is essentially the concept. How we got involved is we were able to, and I'm going to keep this muted, we were able to be the testing lab that invented the grout mixture that sealed the bridge deck together at the end. So what you're seeing here is hydro demolition, taking off the old bridge deck, and then just literally plucking out the old girders to make way for the brand new precast girders. So the precast girders were made off-site and placed in a laydown yard and then delivered to be cast in 1 weekend. So all of this is happening from a Friday night to a Monday morning. And I'm going to pause it here at one moment, but what you see now is them putting down the panels, the precast panels. So I'll pause right there. These are precast panels that were also made. And then as you notice, these precast panels have seams in them. So the one product that had to be made on site in a ready mix truck was the material that would seam all of these panels together. But they wanted to be able to put traffic on this on a Monday morning. So from Friday night to Monday morning was the construction cycle. So they got MTSU's lab to invent the grout mixture that would seam all this together. And it had to get 4,000 PSI in 3 hours. So ultimately, we were able to do the job and they were able to repair 8 bridge decks in greater Nashville with this material, with this process. And so when the red ready mix trucks show up, that's the grout mixture that you can see going in and sealing up these panels. And then ultimately they were able to pave it and then open it up for traffic the next morning. It really is a beautiful project. And they did this 8 times over in one summer. Memphis has done this as well. I've heard Knoxville is next on the list to start doing some fast fix bridges, but really exciting to have a concept like that work in Tennessee, and to fix a bridge in 52 hours is amazing. So this project's pretty near and dear as well. This is just right up the road. If you come to Nashville very often, you've probably traveled on 440, and the 440 loop around Nashville is very congested. It was built long ago where it was more built with 2 lanes with a nice grass median in between. So you had 2 lanes, large grass median, and then another 2 lanes. They call that a parkway instead of really an interstate. Well, 440 has been long an interstate and not a parkway. So they decided to go in and literally take up all of the grassy median and turn it into more drive lanes. Much like you see Atlanta has done, we're trying to do the same thing. What I love about this project though is, and I will tell it to anybody that asks, is this is a huge environmental effort here. They basically ground down, or I'm sorry, rubbleized, not ground, but rubbleized all the old pavement, all the old concrete pavement into large boulders, into 57 stones and 67 stones, and turned it into, so this is the grassy median that was, they tore up all the old concrete pavement, put it in the median, and then basically ground and crushed all of the old pavement into new aggregate, recycled aggregate, to put under the new asphalt road. So they had to truck in 0 virgin aggregate for this project. They reclaimed every bit of the aggregate for this new project. So really, really exciting that Tennessee has been able to accomplish a project like this, because that is, 8 miles of roadway that has now been using or has used recycled concrete aggregate. I just drove on 440 the other day. The project is complete now. And it's just exciting to drive on this beautiful asphalt road that has been built on top of recycled concrete aggregate with a cement stabilization to make sure that nothing moves and nothing gets penetrated with water, and then asphalt on top of that. And this was the large gantry crane that was used to build the bridge, the 2 bridges that had to be built over I-65. So the bridge itself had a gap in between, and they came in and inset new bridge panels to have 2 more lanes of traffic on a bridge that was already built. So pretty neat that they were able to basically build a bridge in the sky in between 2 existing bridges. So that was also a very unique concept, this bridge in the middle concept, where they didn't take anything down, they just added to it. So pretty neat. So I mentioned cement stabilization. So my nod to professors there at UTC is I'm working with UTC in the civil engineering department on continuing this thought of stabilizing roadways. So we have a research contract right now with TDOT. UTC is the lead PI, and I'm a subcontractor on the contract, where we're working with them to figure out more roads that we can stabilize around the state of Tennessee to allow our asphalt roads to last longer. So far we've investigated 2 different roads around the state, but essentially this is where the magic happens right here. This is a reclaimer. And this reclaimer is basically grinding this road into subgrade material, subbase and subgrade material, so that you're not having to truck off any material or bring any new material on. And so the concept really is about grinding the road in place and then sprinkling cement on the road, watering it. So you got your water truck there, and then coming back over it with your final paving surface. What we're seeing already is really good rideability numbers, really great deflection numbers. And we really feel like for high traffic areas, this is going to be a great technology. So I'm happy to work with UTC on this. And I just want to remind everybody that, as you get into your career, it's always good to get outside of this country to see how, construction is used in other places. It's really amazing, how many countries are doing things even better than the US. You go to Europe and you see how their homes are built and their apartments are built. I mean, in some cases, they're light years ahead of what we do here. So I try to get out and travel other countries and just see their construction processes. And I've been really proud of a project that we've done in the Dominican Republic, where we've helped restore their reef with artificial concrete reef. And that's been a project that I feel like is really helping the environment in a different way. They've been also hit by several hurricanes, and their beaches are eroding away. And so we've been down there about 5 summers trying to make sure that we're helping, save their beaches essentially. Otherwise, they will not have a tourist industry and not have a way of life, because they're primarily tourism. So we've been able to actually scuba dive our reef down and create this reef. And I've been taking students every summer. We stopped going actually in 2017 due to hurricanes, and we haven't been back in a couple of years, but hopefully we'll be able to go back very soon. So that's a long and winded conversation about some of the work I do here. I've really enjoyed able to share it with you. I hope I've sparked some interesting ideas, and I would love to hear from you. I'm easy to find, heather.brown@mtsu.edu. If you have any great ideas or just want to chat, I'd love to hear from any of you. So thank you.
Thank you so much, Dr. Brown. We appreciate it.
Certainly.
And I know we are just a little bit over time, just a couple
Sorry.
minutes. So great presentation. Thank you so much. But I wanted to say that just for our questions and answers, if there are any hot questions. I think we could fit in a couple, but wanted to give students a chance for that, but just let everybody know if their schedules. So any questions, feel free to type them in the chat box, or you can unmute yourself and ask the question. I do have a couple that were submitted offline. First is, what do you see as the obstacles to using glass in concrete applications?
Certainly. Right now, I think the biggest obstacle is that much of the glass that we could use is really contaminated glass. So the first really direction is you've got to have a manufacturing facility that can chemically clean the glass before it's usable. So right now, if you're going to just ask for glass in concrete, you would actually have to go to a manufacturing facility that utilizes glass in their processes and use glass that hasn't been contaminated yet. So let's think about that, like windshields in a car. Ford Glass Company makes windshields every day, and their glass has not been contaminated yet. So we could get their leftover glass product, anything that they throw away, and we could put that in concrete today. But we're not really finding that there's facilities that will receive it and maybe grind it or grade it appropriately. So we're sort of missing the middleman. Concrete producers want it, owners want it, and there's recycled glass available, but we need a middleman to clean it and store it and basically facilitate the distribution of it.
Thanks, Dr. Brown. And this might be the last one, but we have a question that came in the chat. How can titanium dioxide be used for concrete despite its high cost?
Right.
And what would be the best use for it?
Sure. So titanium dioxide is expensive. I think I quoted, something around 10 times that of a normal concrete. And I'm not really sure what would bring the cost down except demand. If a lot of people demanded it, I can imagine that we would have more competition and therefore cost would come down like anything. But really the best use for it is really those two concepts of self-cleaning and smog eating. So most definitely you're going to reduce your SOx and NOx that are in the air, all of your harmful chemicals that are in the air due to just industries and factories. If you can build infrastructure that strategically places titanium dioxide in areas that have, let's say, low air quality, an Atlanta, a Houston, if you can find areas that struggle with clean air, you could strategically use titanium dioxide at that 8-foot level, so sides of buildings, sidewalks, pavements, and really help clean the air before it makes it up into the atmosphere and ultimately cutting down on greenhouse gases.
All right, thank you very much, Dr. Brown.
Mm-hmm. Sure.
All right, looks like we had one more come in, if that's all right. I hate to leave out a student question.
Sure.
Are there current research efforts in associated concrete applications, such as grout and mortars, taking some of the advancements in concrete and applying them to other concrete use applications?
I think it's a great question because when I talk about concrete, it's great to talk about all cementitious applications. I think grout and mortar, although extremely important, the technology behind those two materials hasn't changed a lot. Grout is something that, is so critical in fully reinforced block buildings that we rely on it heavily, but it's sort of a hidden gem. We don't see grout. Grout is pumped into the core of block, and then there's rebar. And the chemistry and the science behind grout hasn't really changed other than we're able to introduce some of those recycled powders. So some of the things that I mentioned that work for replacing cement would work in a grout and a mortar. The other thing on mortar that I would say, mortar is going to be your material between your brick and block. So that's what we do see architecturally. We see the brick or we see the block and we see our mortar joints. I think what has happened mainly with mortaring is that we've increased or improved, I should say, the permeability and the durability of mortar. Because mortar is one of those areas that's one of the first things you see on a house if there's a problem is a cracked mortar joint. And so just creating mortars that are a little more flexible and move and give with the changing climates is really important. And there has been some advancements in that.
Appreciate that.
Sure. Well, I appreciate the large crowd, so I appreciate everybody coming to listen and staying with me for over an hour.
Yeah, we appreciate you, Dr. Brown, and we're happy to record this so that we can share it on our website and then share it in other ways too. So really appreciate it.
Absolutely.
So I'll open up for Dr. Nasab or Dr. Pack. Any departing words? Oh, you're muted.
That was an excellent presentation. Thank you, Dr. Brown, and we should give her a round of applause. I know she
Thank you.
cannot hear us. But
Thank you.
thank you.
Appreciate
Very
it.
much.
All right. Well, everybody have a great day.